Today I'd like to talk about rates of change and kind of introduce you to derivatives. And actually, rates of change are something that you've already dealt with in life. So if we have the rate of change of y with respect to x, that's just going to be the change in y over the change in x, which you can also write as delta y over delta x, and that should look familiar to you. That's basically slope, right? Likewise, if you read that x changes from a to b, then y changes from f of a to f of b, well, that again is that delta y over delta x is just going to be equal to f of b minus f of a over b minus a. Again, that's slope. You are familiar with that. So let's take slope and apply it to some situations here. After a person exercises, their rapid heart rate decreases as the time passes. Let h of t represent your heart rate. Write an expression for the rate of change of your heart rate over the period from t equals 0 seconds to t equals 90 seconds after you have stopped exercising. Well, to talk about that, our change of our heart rate with respect to time is just going to be our heart rate at 90 seconds minus our heart rate at 0 seconds divided by 90 minus 0, which if we wanted to simplify, we could write as heart rate of 90 minus heart rate of 0 over 90. And that would represent the rate of change of our heart rate. Let's talk about another example. Let's see if I can get this caught in here. A roller coaster has its largest drop modeled by the equation below, where d of t is measured in feet and time t is measured in seconds. D of t equals 1.87 t cubed minus 20.64 t squared plus 112.79 t plus 132.56. We are asked to find the average speed of the roller coaster from 4 to 6 seconds. Well, to do that, our average rate of change, which I'm going to write as AROC, average rate of change, is equal to d of 6 minus d of 4 over 6 minus 4. And I've already calculated this for us. So this is approximately 470.18 minus 373.16 divided by 2, which simplifies to about 48.51 feet per, ft per second. Well, we're also asked to estimate the instantaneous rate of speed, instantaneous speed of the roller coaster at exactly 5 seconds. Well, at exactly 5 seconds, we don't have a formula yet to calculate that speed. So we're going to calculate our instantaneous rate of change, IROC, by just using 5 and 5.001, right? It's not exactly 5 seconds, but it's very, very close. So our instantaneous rate of change is going to be equal to d of 5.001 minus d of 5 over 5.001 minus 5, which is approximately 0.046647 over 0.001. I almost wrote a 6 there. 1, which is about 46.647 feet per second. I want to take a moment here just to note that when you are writing on the AP exam, you can lose points for not labeling on your free response questions, so we will be doing that throughout the course. So the instantaneous rate of change at x equals 5 seconds, instantaneous rate of change at x equals 5 seconds is approximately 46.647 feet per second. Also note that I use 3 decimal places. So labeling, 3 decimal places. You need both on the AP exam. Do not forget that. So let's look at rate of change kind of graphically for a little bit here. Not there yet, but here. Here we have a graph of a car moving. This is, I didn't label this, but this is a car moving. We want to find the average rate over the 2.5 hours here. So you can see that we start at time is 0, and then we go looks up to like 150 minutes here. This is our time in minutes. This is in minutes. We want to find the average rate of change over the 2.5 hours. Well, to find that average rate of change over this whole time, we're going to take f of 150 minus f of 0 over 150 minus 0. So that's going to become 30, right? F of 150 here is 30 minus f of 0 is 0 over 150, which simplifies down to 1/5. All right, well, that's good information to know. So our average rate of change of that car over that 2.5 hours is just 1/5. Well, how fast is the car going between t equals 30 and t equals 50 minutes? And if I look at my graph here, I can see between 30 and 50, actually nothing is happening, right? It's going 0 miles per minute. 0 miles per minute. If it's going 0 miles per minute, it's just stopped, right? It wasn't moving at all. When is the car traveling fastest? Well, it's going to be traveling fastest when we have our steepest slope, which to me looks like between 0 and 30. So when 0 is less than t is less than 30. And then again between 50 and 80. And then when 50 is less than t is less than 80. These look to me to have the same slope here, and if we calculated that, we would find that it does. When is the car traveling slowest? Well, it looks like it's going the slowest, and it's actually traveling, not just stopped, between 100 and 150, right? So when 100 is less than t is less than 150. How fast is it going between 100 and 150? Well, if I go up here, I can look between 100 and 150. I'm going to calculate this using rates of change. So f of 150, can you see this? I'm just checking. Yeah, f of 150 minus f of 100 over 150 minus 100. Well, f of 150 is 30, 100 is 40, over 150 minus 100 is 50, so that gives us negative 10 over 50, which simplifies down to negative 1/5. Speed cannot be negative, right? Let's take the absolute value of that, so we get 1 mile per minute, per 5 minutes, excuse me. I gotta rewrite that. 1 mile per 5 minutes. And if you convert that, you will find out that that's 12 miles per hour. 12 miles per hour. So why is this going, did I do that correctly? When is it traveling slowest? And when is it traveling slowest? And how fast is the car going? Why is it negative there? Why is it actually negative? Take a moment and think about that. And actually it's going negative because the car is turned around. The car is turned around. It's going opposite direction, right? Well, what about speed of the car at t equals 20 minutes? What's going on there? Well, at t equals 20 minutes, right, we're going to take f of 30 minus f of 0 over 30 minus 0. So that is equal to 20 minus 0 over 30, which equals 2 miles per 3 minutes. And if I multiply that by 60 minutes, I get 40 miles per hour, right? And actually, if I did this again, at 70 minutes, which is between 80 and 50, so I can take f of 80 minus f of 50 over 80 minus 50, 40 minus 20 over 30, 2 miles per 3 minutes, which again is 40 miles per hour. Right? So we can see how rates of change allow us to actually calculate speed and time, and can be applied to a lot of different situations. Well, we still want to talk about another type of path, all right? So suppose an object is projected from the top of a 112-foot building, and its path is defined by the equation 112 plus 96t plus 16t squared. And I've actually graphed that for us here. It's a pretty rough version of the graph. And then here I've written down what f of x is at different points in time, right? So if I have this at 1.8 and 2.2 seconds, you can find the average speed by calculating this. And if you put it in a calculator, you'll see that this goes out. But what if I actually wanted to find the speed at exactly 2? What's that rate of change at 2? The average rate of change at 2. Well, in order to do that, it's still a rate of change. It's not just where it is in time, right? So I could get even closer here by using what's called local linearity and getting 1.97, 1.98, 1.992, 2.01, 2.02, 2.03, and you can see that this becomes even more accurate, right? So up here, if I wanted to find the average rate of change at 2, maybe I could use like 2.2 to 1.8 or 2.1 to 1.9, but now I can use numbers that are even more precise, right? So what I want to do is draw what's called a tangent line to the curve at this point. I can draw a tangent line, right? This is called a tangent line. Oops. And that tangent line, I can't do it here because this is all just basically analog, but if we were able to zoom in closer and closer and closer on this graph, here we can see that the graph is curved. But if we got in very, very close, we would have what almost looks like an exactly straight line at 2, right? And at that exact straight line, so let's imagine here's the point 2, right? And it's like ever so slightly curved, we would be able to draw a line and use a point here and a point here to actually calculate the rate of change there, right? And you can get closer and closer and closer. And that, my beautiful students, is what derivatives are. And we will be using those further in this chapter. All right.